Welcome to part 3 of the video podcast series having to do with the use of mass ratios in chemistry. In part 1 we looked at applications of the law of definite composition. Part 2 we looked at applications of the law of multiple proportions. And in this part 3 we're just going to do some A-level problems and see how you do with those. These are the type of problems that you're going to encounter in college chemistry, and this is the best way I know of to help you get ready for that. So stay tuned. A-level problems are such that it will often take more than one slide to present the entire problem. So we'll start it. An analytical laboratory receives 3 samples of compounds containing iron, which is symbolized by Fe, and oxygen, which is symbolized by O. Data obtained from the use of separation techniques reveal the following. In sample 1, we have 6.35 grams of iron and 1.82 grams of oxygen. Sample 2, we have 13.12 grams of iron and 5.64 grams of oxygen. And finally, sample 3 has 7.85 grams of iron and 3 grams of oxygen. So continuing with the problem, we want to determine the mass ratios of the iron and oxygen in each sample. And if the formula in sample 1 is FeO, which is iron 2 oxide, find the formulas for samples 2 and 3. So we look at our solution, and one of the things that I'm going to give you a hint on here is this. In part 2 I talked about when you make a choice as to which compound will have the fixed mass when you're comparing compounds that contain the same 2 elements only in different proportions. And I said that one of my biases is that I tend to choose the metal as the element with the fixed mass, and that's what I'm going to do here. Now, I want to re-emphasize, in the future we're going to find mole ratios rather than mass ratios. When we find mole ratios, we always divide the mole quantities by the smallest number of moles. That is absolute. In mass ratios, in these type of problems, we have a choice. I arbitrarily make the choice that it's the metal. I think by the time we're done solving the problem, you'll see why. So for sample 1, I have my 6.35 grams of iron divided by 6.35 grams of iron, so I get 1 for the iron. The oxygen is 1.82 grams of oxygen divided by the 6.35 grams, which gives me 0.287. So in sample 1, for every 1 gram of iron, I have 0.287 grams of oxygen. In sample 2, for every 1 gram of iron, I have 0.430 grams of oxygen. And I'll let you just look at the way that I solve that rather than reading through it. For sample 3, I have 1 gram of iron for every 0.382 grams of oxygen. So, re-emphasis. In sample 1, which we know to be FeO, there's 1 gram of iron for every 0.287 grams of oxygen. In sample 2, there is 1 gram of iron for every 0.430 grams of oxygen. And in sample 3, there is 1 gram of iron for every 0.382 grams of oxygen. To determine the other formulas, because we can look at this now, since their mass ratios vary, these are not the same compound. Samples 1, 2, and 3 are different from each other. So to determine the other formulas, we're going to find the mass ratios of oxygen, and we're going to do this by dividing each of the masses of oxygen by the smallest. So here we have our different masses of oxygen. We're going to find our ratio between them. In sample 1, obviously, the ratio is 1, 0.287 grams divided by 0.287 grams. In sample 2, the 0.430 grams divided by 0.287 grams gives us a mass ratio of 1.5 grams of oxygen in sample 2 for every 1 gram of oxygen in sample 1. And finally, in sample 3, our 0.382 grams of oxygen divided by 0.287 grams of oxygen in sample 1 gives us 1.33 grams of oxygen in sample 3 for every gram of oxygen in sample 1. Now I can write a formula based on these mass ratios, so here they are. Sample 1 I already know, it's FeO. Sample 2 would be FeO 1.5, and sample 3 would be FeO 1.33. We know in sample 1 that the oxygen, the 0.287 grams of oxygen, represents 1 oxygen for every iron. So in sample 2, with that amount of iron being fixed, there would be 1.5 times that amount, or 0.430 grams of oxygen, which is why we put the FeO 1.5, and it follows through for sample number 3 as well. Now, one of the things that we know is you can't have part of an atom. So the formulas for samples 2 and 3 are not correct at this point, but we have a starting basis to find them. Now, we look again at these formulas we've written so far. They're not complete for samples 2 and 3, as we discussed earlier. Dalton's atomic theory states that atoms of different elements combine to form compounds in whole number ratios. So what we're going to do here is we're going to multiply the subscripts in formulas 2 and 3 by the smallest whole number coefficient that will produce a whole number subscript. So that's what we're going to do next. In order to get 1.5 to a whole number, we're going to multiply it by 2. And when you multiply the subscripts in these chemical formulas, you have to multiply both of them. Now, iron doesn't have a subscript written because its subscript is 1. And in chemistry, we don't write subscripts of 1. But you still have to multiply that subscript of 1 by 2. When we do that, we get Fe2O3 as the formula for sample 2. For sample 3, to get 1.33 to a whole number, we're going to multiply it by 3. And so we're going to multiply the iron subscript of 1 by 3 and the oxygen subscript of 1.33 by 3. When we do that, we end up with a formula of Fe3O4. So our correct chemical formulas based on the sample data that we have, sample number 1 is FeO, sample number 2 is Fe2O3, and sample number 3 is Fe3O4. We have been working on A-level problems having to do with mass ratios. This is the end of part 1. Be sure to watch part 2 as well. We'll do another problem together that is a high level of difficulty and will help you prepare for college chemistry. I want to leave you with a quote by Holocaust survivor and novelist, author Elie Wiesel. This quote will mean much more to you if you read it yourself. So I would encourage you to read it out loud and absorb it the best you can.